Hey kids, look who we have here. Oh, hello, sir. Hello. You're looking mighty fine. He's got a big brain. All right, cool. Right. So today is gonna be special. I was thinking about how we were gonna do the cube, right? I was talking about that last lecture, and my first plan was to just inline it, like we've been inlining these planes. So we would essentially write, a really a really big array of vertices and then put it in a VAO and render it. That's what I did last time, and while it was, I know it wasn't fun actually. I don't know why I was even gonna say that. It wasn't fun. It was annoying, and it was a bit boring because in the end, all we had was cubes to do everything. So if we wanted to do a little scene, we could only do it using cubes, and when we did lighting, we can only see the lighting be applied to cubes. So it was quite boring. So I thought, okay, let's do some model importing, but I don't want to use a library like Asimp or something like that because they're usually incredibly annoying to set up. Some of them are DLL only, and also, it's not like you just import it and it's done. There's actually a lot of massaging you gotta do with the data to actually get it into OpenGL, into like a usable format. So even then, I was like, okay, that's annoying. So I thought we would just write our own in that case, write our own OBJ importer, wavefront object files, because they're quite easy to import. So that was my plan, so I started doing that, and while I was writing it, I was saying like, okay, this is taking a long time, and it's not really important either that you know how to import an object file, how to parse files in C++. It's not really interesting per se. So what I ended up deciding to do is to just keep the code that I wrote and just send it to you guys. So I will send you a wavefront importer, essentially. Let's see. Let's just close these. No, I don't want to save this. No, I don't want to save that either. I don't want to save that either. Okay. Lost my train of thought. Oh yeah. Okay, so I'll show it to you. Here it is. So, we're just gonna have these. Okay, there it is. Yeah, there's actually a header. So here's the header and here's the source file. So it's not a lot of code, but still, it was annoying to write. So I will include these two files in our project. So if you're curious, you can go in and have a look, have a peek at how I set it up. But otherwise, we're just gonna call, the functions and use them, and that's gonna be it. And I've done some nice things of like making sure they're aligned in a nice way. They all use GLM vectors, so we don't have to do any sort of conversion there. And I've triangulated all the models for us, so we don't have to worry about only using triangulated meshes. It can handle any n-gon. Cool. So let's include it in a project. So I'm just going to take these two and let's see. Graphics score source. I'm just going to put them in the source folder here. There we go. So I got to make sure if I go into Visual Studio here, I have to make sure to include these two in the project here. So I used include in project. Make sure you have show all files on or you won't even see them. Whoops. Or you won't even see them here. So now they're here and they should be compiled. So let's see if I can hit compile. Yeah, it worked fine. Very good. So let's just take a little peek at them. So I included here, I'm gonna include some, I'm gonna remove this material files from those. I included some assets for us to play around with. I have the cube, obviously, then I have the monkey face, the blender monkey face, and then it's a sphere. Let's look at the cube because that's quite easy. No. Okay, well, okay, this is what it looks like. Very cool. I want to open it up in a text editor though. Let's go Sublime. No, I don't care. No, stop. Okay. So okay, so the way it works, it's the purpose of wavefront. I'm stammering. The purpose of wavefront object files are to be easy to parse. They're human readable, so you can open them up in in Notepad or a text editor, and you can read all the contents of it. It's supposed to be human readable, and because they're human readable and because of how it's sort of aligned its data, it's very easy to parse. You know, it doesn't matter which language you are working in, Python, C++, or whatever. It's always going to be easy to make, you know, a few lines of code to parse this into data. So we have the vertex positions, so then we start with a V, and then we have the texture coordinates, so that's VTs, texture coordinates, or UVs. And here we have the normals, so VN means normals. And here in face, so F stands for face, and it defines a group of vertices. And unfortunately, it doesn't really work with elements, so it doesn't define vertices and then makes faces with vertex indices or elements. What it does is it defines the vertices right here by which index of position, texture, and normal it has. So here's a face, and here is the you know, combination of position, normal, and texture coordinate to make one vertex of that face. So you have sort of indices for each of the attributes, and unfortunately that doesn't work with OpenGL. Their elements have to describe one complete vertex. You can't have elements for one for normal, one for position, one for texture coordinate, as far as I know, at least. Other file formats like FBX arrange their vertices as exactly that, as vertices, so they will have, you know, one vertex where the position, normal, and texture coordinate is defined, and then another vertex where position, normal, and texture coordinate is defined, and then you have indices describing, you know, what the order of the vertices to be rendered. So that's much easier to import into OpenGL and DirectX. So unfortunately, we can't use element buffers for object files, because, you know, that's just how they're laid out. Cool. So this is what it looked like, and my parser will essentially just give you that. It will just give you an array of positions, an array of texture coordinates, an array of normals, and then an array of triangles. All right, so it will split these faces up into triangles. So in this case, it's only quads, right? Every face has 4 vertices, so it's only quads. So we'll split them up into 2 triangles, and I will use the triangle fan method. So, you know, it will take the first, second, and third, and then I will take the first, third, and fourth to make 2 triangles. And then it uses that algorithm for every subsequent vertex after that, if there's more than 4. And here's, you know, how many triangles there are. So a triangle struct is just 3 vertices. So a triangle is defined by 3 vertices. Excuse me. Yeah, and then every vertex has an index to its position, its texture coordinate, and its normal. So it's you know, laid out exactly like the object file is. It just sort of parses it down into data, so it's easier to work with. Okay, so let's try it out. So we just gotta call this like wavefront load here. So I will just let's actually make a new file for this. Let's make a new file for mesh, so we can put this code somewhere neat. So I'll just make a mesh header, and then I'll make a mesh C++ file, like so. All right, so we'll do a mesh load here. So that will load the wavefront file and convert it into an OpenGL mesh or a VAO for us. So it will do both of those steps. All right, so I create the implementation here. So let's import or include our wavefront, and then we'll call wavefront load path. So that will return a pointer to a wavefront file. I'll call it object. Why not? Cool. So let's check it out. Let's just break here so we can look at this. So I will go into main and include mesh, like so. And then we will, I don't know, put it somewhere down here. It doesn't really matter. Yeah, I'll put it here, I guess. Mesh loading. Mesh load. And then I'll do, let's do assets cube.object. Like so. Let's check it out. Whoa, null. Why did I get null? This microphone is not the best for like drinking tea. Hold on, the focus on my video is going crazy. There we go. Okay. So why am I getting null? Well, it's because I misspelled the path, right? I put a second J there. I bet you guys were like, "No, what is he doing?" Well, it was on purpose. See, I'm smart. So I have defined it. So if the file fails to load, then it just returns null. So I'm just gonna check for null here. So if object is null, then I'll just print like failed to load mesh file. It doesn't exist, I guess. I'll write that. I don't think there's gonna be any more errors in the wavefront on this return. So now if we play, oh, I didn't put the string path. There we go. So if we play, hopefully we should get, yeah, okay, so it failed to load the mesh asset cube object. Well, doesn't exist, and then sad smiley. So cool, so now I can go back and actually make the correct path. Like so. And now, okay, let's actually take a look at it. There we go, it's not null. So, well, unfortunately, it's, you know, it's, there is pointers. So they're not very easy to take a look at. But you can see that, okay, at least the first vertex looks okay. It's like 1, 1, well, I guess, yeah, okay, so 1, 1, minus 1. Let's take a look at the, okay, so 1, 1, minus 1. So the first vertex position looks okay. And then the first texture coordinate should be 6, 2, 5, 5. Let's check that out. 6, 6, 2, 5, 5. Yeah, so that's correct. So it looks fine. Great. So let's start, you know, building our data, okay? Because we can't upload this right now, or we kind of could. We could upload, like, you know, the positions, texture coordinates, and normals as 3 different vertex buffers. But again, remember, it's not aligned, so we can use an element buffer to actually pair these together. We need to actually do that ourselves. So we need to do a little bit of work ourselves. And the way I'm gonna do it is that I'm gonna just build one buffer that has, you know, the interleaved setup we had before, where, you know, position, texture coordinate normal, position, texture coordinate normal, or so on. and then upload that to one VBO and then bind the attributes as interleaved attributes. So I'm actually gonna make a struct for this. I'm gonna use to make a struct vertex. So I'll be, oh, excuse me. So I'll just make a position. There we go. Caught me red-handed. So we have a vertex struct now, which I'm gonna start with position. Let's just let's not jump into this. Let's go. We'd rather jump in the deep end. Let's just start with one thing at a time. So I'm gonna allocate a vertex array. So I'll do verts, and that's gonna be equal to new. That's gonna be a pointer. New vertex, and then okay. So how many vertices do we have in our mesh total? Well, we have how many triangles. We have access to that. I'm gonna put it here. So we can look at that. We have access to how many triangles we have. We have the num triangles here, and what was I gonna say? And okay, yeah. And how many vertices are there per triangle? Well, there's 3, right? Tri means 3, I think. Angles means angle. So 3 angles or 3 vertices in our case, I guess. I should call it triverts. So we can just take object. Oops. And since we're not going to be reusing vertices because we can't use element buffers in this case, we can just take num triangles times 3. All right. So now we've allocated an array of vertices of size object num triangles times 3. What is this? Using operator on a 4-byte value and then casting the result to an 8-byte value. Oh, okay, well, whatever. Thanks. Right, so now we have our array, and now let's start filling in the arrays. I'm actually gonna keep an index here. I'm gonna keep a numvert, yeah. Oops, I immediately removed it. So let's loop through all the triangles. So try index is equal to 0. Try index is less than object num triangles plus try index. Whoops. So let's loop through them, right? So I'll get the triangle. So we'll do a wavefront. Whoops. Triangle. Triangle is equal to object triangles try index. All right. So we're looping through all the triangles, and I'm just getting the triangle here from the array. And then we want to loop through the vertices. Okay, so I'll do another for loop. So I'll do vert index is equal to 0. Vert index is less than 3. So that's hard coded. So we don't need to worry about that. It's gonna be always gonna be 3 vertices per triangle. Because I've triangulated it. So now we're looping through all the vertices of the triangle. So I'll just go ahead and get the wavefront vertex. I guess I'll call that I guess I call it vertex, yeah. So I'll do triangle vertices vert index. I might have made these references if I wanted to, or right now it's gonna copy it every time. Fuck it, let's just make them references, whatever. It doesn't really matter. This will avoid a copy when I'm getting the vertex from the array, but yeah, whatever. Doesn't really matter. I shouldn't have done it. I don't know why I brought it up. Anyways. So now with the vertex structure, this wavefront vertex, that will give us the indices to each attribute, right? So we have the index to the position of this vertex, and we have the index to the texture coordinate, and we have the index to the normal. So I will actually so I will create a vertex struct here. So I'll do new vertex is what I'll call it. And we will do new vertex dot position is equal to object positions vertex index position. Right, so I'm getting the index to the position of this vertex, right? Because if we look at the, for example, the first face here, the first vertex of the first face has position index 1, and that means it takes the first vertex position, all right? The first vertex position, and then it jumps over, whoop, next vertex, it has index of position 5. That means it takes 1, 2, 3, 4, 5. It will take this vertex. So that's the position of the second vertex of the first face, okay? And then it takes the next one, 7. That means it takes the 7th indexed position. So 1, 2, 3, 4, 5, 6, 7, and it will be this one. And that's the position of the third vertex of the first face, and so on. And then for texture positions, texture coordinates or UVs, it takes the second index here, so that's the texture UV index of the first vertex. And then here's the texture vertex, texture position of the second vertex. Mind my words, and so on. And you can see the normal is the same, right? The normal is always 1. And that's because a face is facing one way, right? The front face of a cube will all the vertices of that face will have the same normal because it's flat. It's a flat face. So that's why you see each of the vertices of the first face having the same normal index. And the same thing for the second face. Here all the normals are the same, 2, 2, 2, 2, and then here 3, 3, 3, 3. So each face has its own normal associated, which makes sense because each face of a cube has its own normal. One has normal X, one has normal Y and Z, and so on. And just in case you don't know what a normal is a vector pointing away from the plane, right? So if my hand is a plane, if my hand is, the side of a cube or a side of a triangle really, then the normal will point right away from that face. Always at a 90-degree angle like this. And that's true for like a sphere, the normal will always point, away from the sphere in that case. Or a more complicated object is always, away from whatever triangle it is. And this is, as you're gonna see, this is gonna be insanely useful for lighting later on. Great. So, yeah, okay. So I'm setting the position of this new vertex here. I'm setting the position to be, oh, excuse me, whatever position is at index of the index position, right? So I'm taking this index and looking up in the position array which position that is. And I have converted these to 0-based, by the way. I will say that. That's easy to miss, but yes, they are 0-based. Even though in the file they are 1-based, like heathens. So yeah, you don't have to do -1 here. Yeah, so I'm looking up in the positions array whichever index is of that vertex, okay? So I'm having to do this lookup. And then I'm setting the position of our new vertex here to be that. And then I'm gonna set that position in the array. So I'm just gonna do verts, numverts ++ is equal to new vertex, all right? So I'm just assigning the first array, or whatever array we're on, to be this new vertex. I'm assigning the vertex in the array to be this new vertex. Cool. Hopefully that makes sense. This numverts ++ will increment an index, or an integer, I should say. Depending on where you put the ++ though, this will evaluate different values, all right? So if I write numverts ++, let's do this example code here, right? So value is equal to 0. And then I write value ++ like this. Let's do it 3 times. This will write 0, 1, 2. All right, so even though I'm incrementing 3 times, so at the end of this code, the value will be 3, right? So it will be 0, and then 1, 2, 3, because it's incremented 3 times. The value plus plus evaluates to what the value is before the increment. All right, so here it will return 0. Like this statement will evaluate to 0, and afterwards it will increment value to 1. Okay, so that's why it's printing 0, even though after the print value is equal to 1. And if I instead do this, plus plus value, like so, this is the other way around. This will print 1, 2, 3, because it will increment before it evaluates. So it will increment value from 0 to 1, and then it will also return 1. So it will return whatever the value is after the increment. So that means if numbers is 0, so if we're on the first vertex in the array, this will evaluate to 0. So we will be setting the first vertex in the array, and then it will also increment. So then the next time we come to that part of the code, it will be 1. So then we will be setting, you know, the first or really the second vertex in the array, and it will increment to 3, and then so on. Or increment to 2. So it's a neat little trick, a little C++ trickery. Let's do build vertices from face data in object file. Okay, so now we should have an array of vertices. We should have an array of vertices. Yes, right here, with only positions in this time for now. So how do we proceed? Well, let's make a vertex array object first. So I like to have a vertex array object sort of represent one mesh, okay? So in this case, the mesh will sort of be the vertex array object, or the other way around. So I'll do that first. I'll do create VAO. And also it's good to create a VAO and bind it the first thing you do, so you don't accidentally, you know, bind or change whatever was bound before, whatever VAO was bound before. So if we make sure to bind our VAO before we do anything, then we're sort of safe that whatever changes we're doing those changes to our VAO and not some other VAO. So I'll just do a GLUint VAO. And then GL generate vertex arrays. There we go. It's 1. There we go. That should be good. Oh, we haven't included. Yeah, we're gonna include glue here. There we go. Tick Malin. Oh yeah, it's GL glue. There we go. Okay, cool. So now we're generating our VAO, and I'm gonna bind it right away. So bind vertex array VAO. Cool. And next I'm gonna create our VBO. So create VBO. So I'll do GL gen buffers. 1 buffer, thank you. 1 buffer, sir. And then I'll just upload all of the vertex data. So the nice thing, you might be a bit scared that, okay, we have a struct with this vector 3 in it. How are we gonna, you know, convert that to floats to upload to OpenGL? Because, you know, in the main function where we did like sort of inline meshes, here we wrote floats. So, and that's what, you know, what OpenGL expecting is it's expecting floats, because that's what we bind our attribute to. So do we gotta do some conversion or something? Well, no, because I know that this vector 3 struct only contains 3 floats. That's all it contains. It contains nothing more. So that means if we sort of look at, you know, the data as is, you know, let's just fill this. You know, we have some data here in memory. Then if we wrote a couple of floats, then, you know, we would have like 0.2, 0.3 maybe, and like 1.5, and 10.0, and so on, bunch of data. That's how we would like sort of inline our mesh before. We would just write the float one at a time. With the vector, however, a vector contains 3 floats. So it will sort of, one vector will allocate the size of 3 floats and then have them, you know, in a row. So it will be like, you know, 0.1 and then 0.3 and then 1.5. So that's the first vector, and then it would be the second vector, so like 10, and 5.2, and, you know, whatever, -1, and so on, and then the next vector. So, okay, so the float point array has, you know, one float, then one other float, and then another float, and then another float, while the vector array has one vector and then one vector. But as far if we only look at the memory, like if we don't know what the type is, if we only look at the memory as is, there actually is no difference between these two. You know, we have the type, so we can sort of, you know, get the X, Y, and Z component a little bit easier. But if we just group these into blocks of 4 bytes, then the floating points actually line up exactly. So, you know, this 0.1 is equivalent to that 0.1, this 0.3 is equivalent to that 0.3 and 1.5. There's no special float, it just floats. And it's just 3 in a row. So that means, as far as memory-wise goes, and as far as, you know, OpenGL cares, it can't tell the difference between we send in a vector 3 pointer or we send in a floating point pointer. It doesn't know the difference. All it sees is the raw memory data. That's all it cares about. So that's why we can actually send in a vertex array, a vertex array that contains a vector 3 in it, because the data in it will be exactly the same as if we had just, you know, made a giant floating point array. It will be the same as far as OpenGL cares. So that's why when we actually upload the data later here, so we'll do GL buffer data. We're gonna bind it first. Bind buffer here. So GL array buffer VBO. And then we can get some buffer data going. So array buffer size. So the size, well, we could count the number of floats. You know, we could do, okay, it's 3 floats per vector 3. And then it's, you know, it's 1 vector 3 in a vertex. And then, you know, okay, so, and then there's numverts, number of vertices. But we could actually just get the size of the vertex, because again, the size of one vertex is just equal to 3 floats, because that's all the data that's in there. So the size of one vertex is just going to be equal to that of 3 floats, because memory-wise, they are exactly the same. So that's why we can just do size of vertex, and okay, and then we have to times that by how many vertices there are. And lucky us, we have this numvert here that we have been incrementing, right? So at the end of this loop, when this has been chugging along for the whole mesh, this numverts is conveniently gonna be how many vertices have we inserted into the array, right? Because we keep incrementing every time we insert a new vertex. So I'm just gonna times it by numverts. All right, and then it's the data, and then and there again, I'm just gonna go I'm just gonna pass in the array as is. It's a const void pointer, and that's, you know, by design. That means you can push any pointer in there. It doesn't care what type it is. All it wants is just a pointer to memory, and then it will upload that to OpenGL. So that's why we can just insert any pointer to any struct or whatever we want, and it will just read the data. So that's why I'm sending in a pointer, which is our array, and you know, it will treat it as it is. If it's floats or if it's integers or whatever we specify, it doesn't care. And I'll do a static draw for the usage. Okay, cool. So now we have a VIO, we have a VBO. Now all we gotta do is bind the attributes, okay? So bind attributes. So I'll use bind the position now, because that's all we've saved. So I'll enable it first. Enable vertex attrib array. So that's gonna be attribute index 0. Then I'll do vertex attrib pointer. This is exactly what we did in main before. So index, that's the attribute index, this is 0. And then size, and that's how many components there are in this attribute. And that's components, that's not size in bytes, that's how many components there are. How many floats, how many integers, how many bytes, whatever type it is. In this case, it's type float, but we don't care about that. It's only how many components, and it's a vector 3. So that means it's 3 components. So size is 3. It's a 3D attribute. And then here's type, and we have floats. It's GL float. Normalized, again, we're gonna type false in here. Stride. Let's just do 0 for now. So we're gonna put stuff in here later when we have more attributes, but for now we only have 1. So in that case we could do 0, 0, and if we just do, if you remember from the attributes video, it's just gonna take them sequentially. Whoops, I bumped my microphone. Cool, so it has succeeded. So how sweet. But we're not returning anything, so we gotta get something out of this function so we can actually use it. And I'm actually gonna make a mesh struct. Mesh. You can make a class if you want to, it doesn't really matter. So I'll make a struct mesh, and in there I will put our VBO, not VAO, because that's what we need to render it. So we need to bind whatever data is in there. And I'm also gonna we're also gonna need the draw count, okay? Because a VAO doesn't know anything about how many vertices there are. It only knows the bindings and you know, what element buffer is bound. It has no idea how much data there is. We actually need a draw count at the draw call to draw it properly. So I'm gonna add that as well. So I'm gonna return a mesh struct here. I'm just gonna do a plain struct, so yeah, we don't really need to allocate anything because the allocation happens on the GPU anyway, so there's a bit of a waste to allocate for 2 ints. I mean, at least I think so. I guess it's sort of a design question, but you're free to allocate if you want to. Okay, so we're gonna return a mesh struct here. So let's see here, we're gonna, if we fail, we'll just return a default, I guess. So at least return a default mesh. And then here, I'm gonna create a mesh here, mesh struct, and then I'll do mesh. VAO is equal to VAO, so I'm just setting that to the VAO, not too rough. And then draw count, and that's how many vertices it's gonna draw. All right, and I'm just gonna put num-verts in there because that's how many vertices there are. And there we go, and then I'll return it. Oops. Oh yeah, okay, so that we got an error because GLU int doesn't exist here, so I'll just include GL glue, like so. Ah, there we go. Perfect. I'll make a draw function as well, why not? So I'll do a mesh draw here. I'll do a const reference mesh. It's always nice to make your systems complete in some way. So to draw the mesh, we're gonna bind vertex array. We're gonna bind its vertex array, and then we're gonna GL draw arrays. So we have triangles. And what's the count? Well, it's the draw count, like so. Very cool. Very cool. So, okay. So now this looks pretty complete to me. I don't know, maybe we missed something. We will see pretty shortly. So here where I load the cube, I'm gonna save that. So I'll do cube. So I'm saving the mesh here. And then let's comment this out. So let's comment out so we have a clear scene. So I'll do like so. I want to keep this, but I'm just commenting out where we're drawing to quads, okay? Because we don't want to use that anymore. Okay, so good. We have a clear scene, so there's nothing here. So now we're ready to actually draw our cube. So I'll do mesh draw. Oops. Cube. Doob. Draw a sick old doobie. Okay. That doesn't look good. Well, two things. First of all, I can tell you the reason we don't see anything, or at least I'm hoping the reason we're not seeing anything, is I commented out everything to do with uniforms here regarding the U model. We have the U view projection, so view projection is being set properly, but U model is not being set at all, which means it will just be a zero matrix. And I can tell you that anything multiplied by zero matrix will just become zero. It will be, you know, an invalid vertex. It won't stay in place. It will just zero. Okay. So that's not good. So that means, you know, all our vertices are in the origin. So that it's just not gonna draw anything. So we gotta make sure we have something. We're gonna make sure we have something for the model matrix. So I will just bring this out here. So I will just make a model here. Model matrix, and I'll set that to be the origin. Sorry, I mean identity. That's what I'm looking for. The don't do anything matrix, and that's not the same as a zero matrix. The zero matrix will bring everything to zero. The identity matrix will do nothing. It will just whatever we multiply with it, it will just stay the same. So now we're actually setting U model to be anything. Ah, okay, cool. Oh no. Okay, not cool. So okay, so our cube became a plane. So that's not very 3D. I feel like we didn't go anywhere. We made a lot of work to do nothing. I can tell you our code is fine. I can tell you the fact we're seeing at least a square is a really good sign. That means we're doing everything right, probably. The reason we're a square has to do with our shader. Our shader has not been kept up with our new technology. And let's take a look at it and try to figure out why it has not kept up with technology. Can you see it? It has something to do with our attribute here. What hasn't it kept up with? Well, I can tell you, the reason it hasn't kept up is because our A position attribute here is a vector 2. So that's the reason it has not kept up, because now it's a vector 3, remember? When we bound the attribute, we made it a 3 vector. A vector 3, a 3D. But before we made our shader as a 2D shader. So we're gonna have to patch that. So I'm just gonna replace this with 3. Alright. So let's see what happens. I'm gonna run the game. Okay, it's completely white, so that's not good. Probably a compile error here. So let's see, on line 16 we have an error. So let's check it out. So line 16 here. Okay, so too much data in type constructor. And why is that? Okay, so here we're making a vec4, and we're pumping in a position 0, 1. And this made sense before when a position was a vector 2, because that meant the x and y component will be a position, and then the z component will be 0, and the w component will be 1. But now a position is a vector 3, which means it will set x, y, z to be a position. But then we have 2 extra extra little numbers here, so we're technically making like a vector 5. So I'll just remove the z as 0, because now we have actually a z component in a position, so we don't need that anymore. We'll just set the w component to be 1, which it has to be 1. Let's see. Okay, still white, not great. Let's see. 19 here. Line 19. Okay. Implicit cast from vector 3 to vector 2. Okay, so what's happening here? So we're setting f position to be a position. F position is a vector 2. Okay, remember, we were sending over our position to the fragment shader to do cool fragment stuff. Well, since a position now is a vector 3, it's doing an illegal conversion from a vector 3 to a vector 2, and that causes an error. You know, it could be a warning, but they have chosen to make it an error, which I think is good. So we'll just update our fragment here to be vector 3, or our fragment output. So let's see. Okay, so this is weird. It's white, and I can tell you right now that's a compile error. That's why it's white. But we're not getting any shader. The shaders is not complaining at all. And I can tell you this is because we have a linker error. All right. You remember back in my linking explain video, I explained the difference between a compile error and a linker error. So right now we fixed all compile errors, compares, but we're gonna have a linker error, okay? And let's find out what that linker error is. Let's go into shader here. So linker errors happen here after we link a program. That's where linker errors can occur. So let's we got the shader info log during compile here. So that's where we catch compile errors. But now we want to get linker errors from the program, and we do that using gl get program info log. All right. So this is the same as with the shader info log, really. The only difference is we pass in the program instead of a shader. So I'm gonna pass in program here. And then we have buff size, so that's the same as before with having a buffer. So let's make a static char here, buffer. Cool. So the length of the buffer is 1024, and then length again it returns the length of the info log, which we don't care about. I'll just type null, and then info log is going to be the pointer to the buffer. So we'll do that there, and then we'll print that. Like so. So now we're printing whatever the program result was. So check it out. And there we go. So now we have some sort of something telling us what the linking error was. It's not the most helpful. I'll tell you that it was very unhelpful, actually, to be honest. So let's see, it says vertex info, so at line 10, okay, so that's this F position here. Unknown semantics, attrib 0xy specified for F position. Okay, so this is not very helpful. I don't actually understand what it even means, but I can tell you that at least it's giving a clue. There's something linky error happening with F position. So that means, okay, on their own, on vertex and fragment, they work fine, but together they are not working, and that usually means the output and the input does not match, and that's exactly what it is. If we go into the fragment shader here, so put that there, the input of F position is a vector 2, while the output is a vector 3, and that's causing a linker error. These two arguments do not match. So I will update our fragment shader to take a vector 3. Okay, and there we go. Now it works. So if I go outside, yes! It's a gosh darn cube, ladies. Fantastic. That's awesome. So we have a cube. Cool. Let's get Mm, let's get the texture coordinate in, yeah? So we had a texture coordinate here, and now we're using it, but it's actually fine to use an unbound attribute. It will just sort of give 0 everywhere. So that's why we're getting texture coordinate 0 everywhere. Because we haven't bound that attribute to any data. So let's get the data. You can sort of see why I didn't want to do the object importing on stream, because, you know, just making the dang mesh is taking a lot of work just in itself. So I'm gonna add the texture coordinate here. So I'll do glm vec2 text coord. So I'll just add that to the vertex, okay? Excuse me. So in the vertex here, in the new vertex, I'll also fetch the texture coordinates. All right, so it's the same as with positions, you know. Same as with position, we got the position based on the index of the triangle vertex, and now we're gonna do the same with the texture coordinate index here. We're gonna fetch it from the texture coordinate list, from the texture coordinate array. We're gonna fetch the index that the vertex is giving us. All right, so from the texture coordinate array, I'm fetching the index of the vertex. Cool. So now we have a bigger vertex, okay? So we have position, but we also have texture coordinates. So first of all, I think we should update our binding for position, because if I run this now, it's gonna look kind of strange. Yeah, this looks this looks like a cube to you. I don't think so, because now, you know, the vertex position and the texture coordinate are sort of getting mangled together into one, because we didn't specify a stride. It's just gonna take, you know, whatever data is next. It's gonna read 3 floats, and they're gonna use to read the next 3 floats. It's just that now those next 3 floats happen to be, you know, 2 texture coordinates, and then, you know, the x component of the next position. So we wanted to jump 1 vertex size between every vertex read. So we could do, like, you know, okay, so it's gonna be like size of float times 3, because it's supposed to jump 3 floats, and then it's supposed to jump, you know, size of float times 2. Okay, so this will work, I think. So we jump 3 floats for the position. If you remember from my attribute video how the stride works, it's how many bytes to jump in between each vertex. So we jump 3 vertices for the position, and then we jump 3 vertices. We do 3 floats for the position, and then we jump 2 floats for the UV, for the texture coordinate, and then we should end up at the beginning of the next vertex. So I think this will work. Let's see. Yes, it does work. So now we're jumping the appropriate amount of data to get to the actual next vertex, instead of just reading whatever is next to reading the texture coordinate and stuff. But we're clever. We can do better than this. We don't need to write it like this. We can actually just do size of glm vec3 plus the size of glm vec2. Because since we know now, there is no difference between a vec3 and 3 floats as far as memory goes. There is also no difference between the size of a vec3 and the size of 3 floats. So we can actually write this, and it will also work, because we're smart. There we go. We have still have the cube. But we're even smarter than that, because now we actually have the actual size of the vertex. It is our vertex struct. Whatever data is in our vertex struct, that's the data that's gonna be in memory. So we can just jump whatever the size of this vertex struct is. My god, guys, we're fucking programmers. So I'll just do size of vertex, and that's just gonna be our stride. Super easy. And there we go, we still have the cube. So the size of the vertex struct is just the size of all the floats combined together, because we are so clever. Great. Awesome. Let's bind our texture coordinates. So that is on index 2. So we put the texture coordinate on index 2. So let's do that. So I'll use the texture, index 2. And then so GL vertex attribute pointer is going to be index 2. Let's write this from scratch. Yeah, let's copy and conquer. So we will do GL vertex attribute pointer. Index 2. So that's the attribute index. Size is going to be 2 in this case because it's 2 floats. So it's going to be 2 GL floats. Normalized, again, we're just going to do false. Stride, and again, since we're so clever, the stride for the texture coordinate is also going to be the size of the vertex, because the size of the vertex doesn't change between, you know, normal position and texture coordinate. The only thing that changes is the offsets. Right, but the size of the vertex, how many bytes to jump to get to the next texture coordinate, is still going to be the same. So we can just, again, type in size of vertex. For the pointer, or for the offset, which I like to call it, that's going to be, okay, how many bytes in is the texture coordinate into the struct. So that's going to be, you know, 3 floats, or in our case, the size of GLM vec3, because before the texture coordinate is a vector 3. So, you know, right after the vector 3 is the texture coordinate. So we're just going to write the size of GLM vec3. And unfortunately, it wants it as a void pointer, so we have to cast that to a void pointer. And now, hopefully, yes, there we go, we have textures. Of course, it's aligned, like it doesn't have the UVs where like one side is the full UV plane. It's actually lined up like a what do you call it? Like a folded out cube. So that's why we're getting it like this. But I can tell you this is working fine. So let's see, where is his face? There it is. My God, what have they done to my boy? They've butchered my boy. All right. So cool. So that's that. Let's do normals then. So I will add normals here. So I'll do GLM vec3 normal. So I'll add it, and then I'll, oops, new vertex. I will copy it over from the object file. Normals, vertex, index, oops. Come on, autocomplete, stop. Oh my God. Index normal. So just like with the position, just like with the texture coordinates, I am looking up the normal from the index I'm getting here from the vertex. So I'm taking this index and looking that up in the normals array. So now we have the normal and the position and the texture. So now we have actually all the data we need. And again, you know, if I run this, aha, okay, so the texture coordinates broke because I actually inserted the normal in between position and texture. If I actually if I don't do that, if I move it after the texture coordinates in memory, then it works just fine. Because since we were so clever and we put size of vertex here, as we're loading it with more data, as we're, you know, putting more stuff into it, the size of vertex is just going to adjust to whatever data we added. So the stride is always going to be right for each of the attributes. So now it still looks completely fine, even though we added this, you know, vector 3 to it. The only reason it broke before is because this offset broke for the texture coordinate, because now that's the offset to get the normal. So it was reading normals as if they were texture coordinates. So that's why it broke. So now I think we've got this. So I'm just going to copy this. So I'll change all of these to 1. So we're going to have, oh, no, not that one. We're going to have attribute index 1. Right now it's color, but it's a vector 3, so that's quite convenient. So we're just going to reuse attribute 1. So instead of being color, that's going to be the normal of the vertex. So I'm going to do attribute 1 here, and that's going to be a size 3, so it's a vector 3. It's a float, it's not normalized. In this case, we might want to use normalized. We can trust that it's normalized. from the mesh, so I won't actually turn this true, but I guess in this case it would have maybe helped to use true here to normalize the data, but we can trust that it's normalized already, so we actually do want to keep this as false. Stride always going to be size of vertex, and then here the offset is going to be size of vec3 and also size of vec2. So we're going to actually jump 5 floats ahead, right? So it's 3 for precision, 2 for text score, and then it's normal. So we're gonna do size of GLM vec3 plus the size of GLM vec2. And that's gonna be the offsets. I think I missed one more. There we go. And that's the offset to the normal. Let's see what happens. Okay, so it works, so that's good. It works, however, we're not using the normal for anything in our fragment shader. So let's actually go into our fragment shader and draw the normal. So I'm just gonna at the end here. I'm just gonna O color is equal to vec4 F color 1, because we conveniently pass in the color here from the vertex shader to the fragment shader. So I'll use output that as the color. Now, let's see. Okay, cool. Yes, so it works. So these are the cardinal directions. It's x plus, so plus x, so that's red, plus y, so that's green, and then plus z is, out of the screen, so that's blue. And then these are black, these other sides, because that's going to be minus x, minus z, and minus y. So that's negative, and a negative color is just going to be black. But the colors are correct, and they are, solid for each face. So each face of the cube has the same color, so that's what we expect. So it seems to work just fine. Fantastic. I'm actually gonna rename these colors to just F normal instead. Maybe I'll just do a find and replace. Actually, let's use the color. No, let's not. Let's not do that. Actually, I'll do F normal here, and it's gonna be F normal here. Yeah, O colors is still going to output colors, so that's fine. And here I'm going to do inputs here. This attribute is going to be A normal. The output is going to be F normal, so we're passing the normal to the fragment shader. So F normal is equal to A normal. So I'm just renaming those. Can this go away, please? Okay, there we go. So I've just renamed every input and output. In the fragment in the vertex shader, I've renamed to normal. In the fragment shader, I renamed the input to normal, and then the output is still, I'm still gonna call it the output color, because we are still outputting a color. And hopefully I didn't make a mistake. Sweet. Cool. So let's try and loading the monkey head, because the cube is quite boring. So I will just do let's where are we loading? Here. Okay, so we're a mesh load cube. I'm just gonna replace this with monkey. So okay, cool. There's the monkey. So he has a lot more interesting normal structure, but it looks kind of, his face is pointing towards Z, so that's blue. His side of his face is pointed towards X, so that's just, kind of reddish and so on. And then, of course, his underside and so on is black. So that's what we expect. Hello, monkey. And just to be complete, we can load the sphere. Yeah, and there we go. There's the sphere. Looks very good. Cool. So we have these 3 models. And let's draw them all at once, shall we? So I'll use the boom boom. So I'll load the sphere and monkey. Like that. So I've loaded all the 3 meshes. And then I will... Actually, let's remove this code here. We don't need that anymore. So I'll do draw nice meshes. So I'll draw the cube. And then I'll make another model matrix for the sphere. So I'll do a translate. We'll just do identity right there, and then I'll translate it to the right by 2.5. Let's do that. 0, 0. Like so, and then I'm gonna upload that. So I'm setting the uniform to be this translation matrix, and then I'll draw the sphere. I'll just copy this, and I'll draw the monkey minus 2.5 translated. So it's going to be translated to minus 2.5 units to the left. Upload that, and then draw the monkey. Then let's see. Ah, perfect. There we go. So now we have 3 different meshes loaded from an object file, normals, texture coordinates, and positions. Successfully loaded, bound to attributes, and displayed. So, oh, how nice. Look at me, so happy. Hello. It's creepy. Let's make him spin. I want to spin this man. Time times. Let's make him go fast, man. It's the 8. Around the y-axis. There we go. So I'm just timesing these two together. So I'm timesing a rotation and a translation. The timesing, I'm multiplying. Let's see. There we go. Look at him go. I want to make him go faster. 20. Look at him go. Ow, 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 ow. Okay, cool. So that's mesh loading. So now we have some meshes. And thankfully we have some interesting meshes. You know, you can download your own object files if you want to. Keep in mind that they're pretty small. Like this cube is just 1 unit. Or I'll say its sides are 2 units. This sphere is radius 1. And this monkey boy is 2 by 2 roughly. So, you know, keep your model small. You can maybe import them into... you can import them into Blender or something and scale them down if you want. But in theory, all models should work. Hopefully, if a model doesn't work, you know, I'm sorry. I didn't test my object loading file with every single object file. So, you know, there might be files that don't work. And in that case, I'm sorry. I just tested it with a monkey and I declared that good enough. So, you know, let me know. I can maybe do a patch. But yeah, that should be it. So next time we will start looking at lighting, some basic lighting, and hopefully that will be fun. I think it will be fun. And until then, have a great day.